Okay, so we're trying to derive the formula for how we're going to evaluate a surface integral. So we've gone through the first two steps. We had chopped things and we had approximated. Remember, what we're approximating is a signed volume that I get when I attach a signed height to points on my two-dimensional surface that just happens to live in free space. So I know what I want to do next is I want to add everything up, and then I want to take the limit as I chop things finer and finer and finer, so that I get the correct answer. I'm going to just write up, when I add things up, that's going to give me a double Riemann sum. And then when I take the limit, that's going to give me a double integral. I'm going to just write it up this way, which is expressing things still in terms of x, y, and z. Because remember, Q was a point in free space. It had an x, y, and z value. Okay. And then I'm going to write it up this way, which is expressing things in terms of my two parameters, u and v. P was a representative point in the two-dimensional parameter plane. It had a u and a v value. So working with this, I would get the sum as I goes from 1 to m, sum as j goes from 1 to n, of f of, I'm going to go ahead and write this out in three variables, xij star, yij star, zij star, times delta sij. And then, of course, I take the limit as both m and n go off to infinity. Now, that's taking two limits. And again, we're not actually evaluating things by taking the limit of the Riemann sum this semester. If we were, we'd have to take a look at the rules for when does it matter which limit I do first. In this case, it really isn't going to matter which limit I do first, but just want to make sure that you're alert to the fact that when you're taking two limits, sometimes it does matter which one you do first. Okay, now if I write things up this way, I'm getting the sum as I goes from 1 to n, the sum as j goes from 1 to n, of f of r of uij star vij star times the magnitude of del r del u crossed with del r del v evaluated at that representative point times delta u delta v, which we said is just our delta A. That's the area of a little rectangle in the UV plane. And then, of course, I'm taking the limit as m and n both go to infinity. Now, both of these are limits of double Riemann sums. This simply becomes the double integral over S. That was what we called this surface in free space of f of x, y, z ds. So you can see where that ds comes from. It comes from taking the limit of the delta s, the change in surface area for each little patch. This is actually going to tell me how I will evaluate something that looks like this, because this is just going to be the double integral over d. That was my region in the UV plane of f of r of uv times the magnitude of del r del u crossed with del r del v dA. So essentially we write our height in terms of our parameterization, and then we approximate our surface area the same way we do when we were just finding surface area. It's going to be the magnitude of del r del u cross del r del v times dA. And basically, anytime I switch from integrating d something to integrating d something else, there's this thing that I like to think of as a scaling factor, because this area, which is flat area in the UV plane, is not necessarily the same as this area, which is the area of a potentially curved surface in free space. Okay. But I can say this area is a multiple of this area. Now, it's not necessarily a constant multiple, so it's not that the area is always going to be twice as big or half as big. The multiple of that area, sorry, this area is a multiple of that area. Okay. This multiple is allowed to be a function to take into account the fact that some of the area might be stretching, some of it might be compressing, but this gives me the relationship between the area that I get in the UV plane and the surface area that I get in 3 space. Excellent. Okay. So that's how we're going to evaluate our surface integrals. In the next video, we'll actually do that.